Yeah, welcome to Nonlinear Optics, the last lecture before Christmas this week. We were discussing phase matching, right? So phase matching, very important topic, of course, because this is the only way to make use of nonlinear effects, or virtually the only way to make use of nonlinear effects. So what we were discussing last time are the tuning curves. So first we were distinguishing different setups. So, the first one was critical phase matching, and we'll talk about critical phase matching now for a while in particular. So what you see here on my slide, if we can switch to that, what you see on my slide are representations of the refractive index for the ordinary wave and for the extraordinary wave. For the ordinary wave, it's of course a circle. For the extraordinary wave, it's an ellipse for two colors, namely here for the fundamental. So if we speak about second harmonic generation, then the red one concerns the fundamental, and as we know, for the blue one, the refractive index is larger. So this is these are these blue curves, and when both curves intersect, so in this case here, the red ellipse with the blue circle, then we have the same refractive index for both waves, and this means, if we speak about collinear beam configuration, that we achieve phase matching. Yeah? And what you see here are the two cases for positive and for negative birefringent crystals. So let's ask a few questions here. First of all, I would like to make sure that Pull Everywhere works. And then I would ask a question, well, that kind of I have shown before, where I have already shown the solution, to be honest, but well, anyway, so it works. At least for me, it works. Oh, so there's one who says it doesn't work, but then it's probably not our problem. So at least the problem is not on our side. Okay, now the real question is, most nonlinear crystals exhibit negative birefringence. What configuration would work for type 1 phase matching? Yeah, so for this, it would be good to know what type 1 phase matching is, and it also would be good to know what negative birefringence means. And then the answer is actually clear. So there is one who says, everybody pretty much says that it's OOE, and this is in fact right. So I was the one who gave the wrong answer on purpose here, just to check, that it's more than one answer in A. But let me quickly explain it. And the easiest way, at least I think it's the easiest way to see it, is the following. So if we plot the refractive index as a function of frequency, then we know, of course, that the curve goes kind of up like that. Yeah? And negative birefringence means, well, we have, of course, two refractive indices, and negative birefringence means that this is the ordinary and this is the extraordinary beam. And now if we have here 2 omega, right, so you see that the only way to do this would be in this way. So if we have 2 omega here and omega here, then you see that the small photon would be ordinary. Yeah, so we have 2 times ordinary gives the extraordinary beam. Okay, well, another question here. Namely, if we choose a longer crystal, then I would like to know about the effect on phase matching, on whether phase matching is more critical or less critical, and so on and so forth. Okay, here it is less. So here there's some disagreement. Yeah, so A was now deleted. Okay, well, let's see. Actually, we can discuss it here at this figure. What I did in this figure was to plot the sinc squared function of its typical argument that we derived, namely of delta k times L. Yeah? And so let's write that down. So actually, the last answer was the right one, but we'll see this here when we discuss this tuning curve. So in the figure, we plot the phase matching efficiency as defined in the last lecture, and actually you find already the answer here. Yeah, so we plot the sinc squared of delta k times L, where L is the length of the crystal. So now, if you want to allow here a certain product, then you can make delta k small and have a reasonable length of the crystal. Or if you already have a certain phase mismatch, then you can't afford a long length of the crystal, right? So it is clear that the last answer was right. The longer you make the crystal, the more difficult phase matching will get, right? And the narrower the curves will be. So in the figure, we plot the phase matching efficiency eta equals the sinc squared of delta k times L divided by 2. Well, and delta k for this specific example, I have written down last time, right? And what we need is are the refractive indices as a function of the variables that are of interest for us. In this case, we chose lambda here. Yeah, so on the horizontal axis, we have lambda, and on the vertical axis, we have theta, and in colors, we have eta. Yeah? So we plot the phase matching efficiency here, and this example is for KDP, which is 1 millimeter long. Yeah? So we plot the phase matching efficiency for a 1 millimeter KDP crystal. As a function of lambda and theta. Yeah? So, and the yellow curve is the tuning curve. So this is the curve where we have maximum efficiency, actually efficiency 1 here. Yeah, so the yellow curve is, we have a problem here, is the tuning curve. So now, if you would be, if somebody would ask you, well, let's see, maybe. Okay, yeah. So I shouldn't discuss this because I have another question for you. Otherwise, I would give the answer right away. So here I have actually tuning curves for 3 different crystals, BBO, KDP, and DKDP. And now the question is, suppose you badly need bandwidth, but you're flexible on center wavelengths. Which is an unusual thing, yeah? So usually you are not flexible on wavelengths because you bought some laser and you have that laser and you need to live with it. So which of the 3 crystals would you choose? So let's go back so that you can look at these again. Yeah? So the question is, which of these 3 crystals would you choose if you're flexible on the wavelengths? Yeah, so, but you want to do frequency doubling here. Yeah, so these are tuning curves for these 3 crystals, each 0.5 millimeter thick or so. And now the question is, which one would you choose? Yeah, so most of you choose BBO and some DKDP. I have a guess why this is so. Right, so because some think this curve has a broader width than this one here. Yeah? But actually the point is, if you need bandwidth, then you're interested, of course, in a flat curve here. Right? So BBO would be the correct answer. Yeah, and of course we can derive the tuning curves for any other nonlinear process that you are interested in, say for difference frequency generation. For difference frequency generation, of course, we would have a different formula for delta K, but we just would write that down, plug in the Salmayer equations, and then use your favorite numeric program and plot and make a plot like this. Yeah? And I just would like to write that briefly down. Yeah, so the same can be done. The same can be done with other nonlinear processes. Das wird immer schlimmer hier. So the same can be done with other nonlinear processes. For example, so yeah, the only thing to change, or the only thing to do differently, is to use the appropriate expression for delta K. For delta K. Yeah? For example, difference frequency generation, there we would write delta K of, say, lambda 3, lambda 2, and theta, lambda 1 is then, of course, defined by lambda 3 and lambda 2. There we would write 2 pi and then the ordinary refractive index at lambda 1 divided by lambda 1. Yeah, so this is the phase. Then the same thing for lambda 2. And now plus the extraordinary index of lambda 3 divided by lambda 3. Right? Yeah, and then, as I said, we would do the same thing. Well, we talked already about the bandwidth of phase matching, and now we want to calculate it actually. Yeah, so this would be here the next subchapter, to calculate the bandwidth of phase matching. Let me see what chapter we have in fact. So this would be 6.6. 6.6 bandwidth of phase matching. Of phase matching. Okay, so what we assume is perfect phase matching at the center wavelengths. And then we would, which means that the coherence length there is infinite. And then we would say, well, we allow a certain phase mismatch. So, then we would calculate to which bandwidth this range of phase mismatch that we allow corresponds. So the first point would be, as I said, to assume perfect phase matching at the center wavelengths. At the center, and I use actually frequency. So omega naught, yeah, which means that the coherence length is infinite. And then we define a maximum allowable phase mismatch. Then we define a maximum allowable phase mismatch. As we deviate from omega naught, right? So, which means the delta k of omega naught plus this delta omega, that this should be smaller than some b divided by the length of the crystal. So we have seen already that the length of the crystal, that the product of the length of the crystal and delta k, that this is the relevant quantity, and therefore we divide here, of course, by L. Yeah? So the next thing would be to do a power series expansion. For delta k. So we say that delta k is omega naught, so delta k of omega naught plus delta omega, that this is, of course, delta k at omega equal omega naught. We know already that this should be, or that we have assumed that this is equal to 0. And then we need the derivative of k with respect to omega at the position omega equals omega naught times delta omega. And of course, this delta k prime is by definition the derivative of delta k. Yeah? And now we need to make a choice for B. Right? We are a little bit generous, and we say that B should be 2 pi because, well, in the end I want to choose, I want to cancel 2 pi. This is, so the delta k that we allow is larger than reasonable, which just means that the bandwidth that we calculate is larger than actually sensible. But if then you decide to just allow, well, what corresponds to a phase mismatch for the coherence length, then you just, so you just shrink the bandwidth by the same factor. Yeah, so typically by pi. So what we calculate is too large by a factor of pi or so. So let's write that down. So we generously choose B equals 2 pi. Yeah, so in reality, B equals 2 would make more sense. Yeah? Would make more sense. Yeah, then we would get the coherence length. So, so we plug that in. So we have delta k prime times delta omega. This now should equal 2 pi divided by L. So B divided by L. Right? And this means that delta k prime, and now you see why I've chosen 2 pi, because I don't like the delta omega. I want to have the bandwidth in frequency. So we find that this is equal to 1 over L. Right? Or in other words, the bandwidth is given by 1 over k delta k prime times L. Yeah? And now it's of course interesting what this delta k prime, what this means, what kind of a quantity is this? So let's look at that. Yeah? So delta k, at least for frequency doubling, this would be k3 of 2 omega minus 2 times k1 of omega, right? And then delta k prime is the derivative of k3, position 2 omega, minus 2 times the derivative of k1 of omega. And this then equals 2 times the derivative with respect to 2 omega of k3 minus 2 times the derivative of k1 of omega, right? And then we find that we have 2 times, and now the derivative of k3 with respect to omega and the derivative of k1 with respect to omega. And what is this? The derivative of k with respect to omega. What is this? That's the group velocity. Yeah, perfect. So what we have here is 2 times 1 over the group velocity at this frequency 3, or the, well, in our case it's the second harmonic, and the group velocity at the fundamental. Yeah? And then we can write down a formula for the bandwidth. Yeah, so I said already that it's a little bit generous. In reality, the bandwidth would be smaller by a certain factor, typically, yeah, on the order of pi. Now, it's kind of interesting that the group velocity appears here. So the next thing to look at would be the walk-off. Well, and for this I have a nice figure, a nice photo that I found on Wikipedia. So what you see here is a calcite crystal, and you see here just you see birefringence. And as this crystal shows a little bit of fluorescence, you see the rays or the beams inside this crystal too. So this is interesting, or this is important with respect to second harmonic generation. If you think about what you are seeing here, then the point is something that we discussed in the first chapter, where we said that the wave vector for birefringent crystals in general goes in a different direction than the pointing vector. Yeah, so which means the wave normal goes in a different direction than the energy flow, which means that both are, or that both separate from each other, right? And if you think now about nonlinear processes, it is clear that the fundamental spatially separates from the fundamental if we use critical phase matching. This is, of course, not the case for non-critical phase matching, because there you adjust the temperature such that that you can actually stay on one of the principal axes of the indicatrix. But this is, of course, not the case for critical phase matching. So this is called walk-off, and we can actually distinguish between spatial walk-off and temporal walk-off, which has different, slightly different reasons. Well, for temporal walk-off, it's probably already clear what the reason is for temporal walk-off. So if we speak about temporal walk-off, we mean, of course, pulses. If the laser would be a CW laser, then it would not make any sense to speak of a walk-off of both laser beams in time. Yeah, so if we speak about temporal walk-off, we automatically speak about short pulses. And there it's clear what can happen. So temporal walk-off, what would this be? I thought it's a trivial question. No? Yeah, so they take, both pulses take a different time to go through the crystal. Yeah, so this is one way to say it. And which quantity would be important for that? I didn't understand. No, the group velocity, of course. Yeah, so the different group velocity. And this is kind of interesting because it's the, well, it has appeared here for the bandwidth of phase match of phase matching, that this also appears in the temporal walk-off. But let's discuss spatial walk-off first. So this would be 6.7. Walk-off. Yeah, so this is another thing that limits phase matching or challenges phase matching. So, as I said, we start with spatial walk-off. And for this, I would repeat a figure from chapter 1. So there, in chapter 1, we have actually shown, so here, something from chapter 1, namely that the D field of the electromagnetic wave is perpendicular on K, on the wave vector, right? We have also seen that D is perpendicular on the H field, or magnetic field, as some people call it. H is also perpendicular on K, and H is perpendicular on the electric field. Now, if we plot this, then if K would be horizontal, then we would say, well, as D is perpendicular on K, the D looks like that, right? So this would be the D field. The H field is perpendicular on both, on the D field and on the K, on the wave vector. So this would be H, the H field, and then of course we also have the electric field. And in an anisotropic crystal, the electric field is not perpendicular, is not parallel to the D field. So the E field may go in this direction in general. Yeah? And then we know, of course, what the Poynting vector is. The Poynting vector is given by E is equal to E cross H. So it is perpendicular to E and H, which means that this Poynting vector here would go in this direction. And you see that's a different direction than K. Yeah? So which means that the energy flow here would deviate from, well, for example, from the direction of the wave vector of the fundamental and of the second harmonic. So let's write that down. So bireferentials leads to a lateral, well, the walk to a lateral walk-off between the interacting beams. Yeah, and the reason is depicted in this graph here. Yeah, so the reason in bireferential crystals, when K is not parallel to one of the principal axes, of the indicatrix, so the Poynting vector for the extraordinary beam will deviate from K. Yeah? And one can actually calculate the angle between both. We call it rho. I don't want to derive it here and just write it down. So the angle rho between both is given by rho equals -1 over the refractive index as a function of theta, and then the derivative of the refractive index with respect to theta. Yeah? And the order of magnitude of rho is in the milliradian region. Yeah, so typically rho is on the order, actually just a few tenths of milliradian, is on the order of a few tenths of milliradian. And just to give an example, again KdP, and again at 693 nanometers, right? And then you find that rho is 0.18 milliradian. This doesn't sound much, but of course, after if you have a tightly focused beam, then you quickly have a separation of the fundamental and the second harmonic, and then there's no mutual interaction between these beams. Yeah, consequences of walk-off. One I already mentioned, namely that efficiency is reduced. Yeah, so reduction of efficiency. And the other one is that actually, well, you can imagine, so if I have two beams, and the new frequency deviates from the original beam, and this happens throughout the length of the crystal, then you see that the beam for the second harmonic will be distorted. Yeah, so if you have a nice fundamental beam and you create at the entrance phase of the crystal a nice second harmonic beam, but then you do it like this, right? Then you get an ugly beam out. And so distortion of the product beam. Yeah, another point here is the phenomenon of spatial walk-off is directly related to the finite angular phase matching bandwidth, which is actually apparent from this formula. Yes? So what you see here in this formula is nothing but the refractive index so the derivative of the refractive index is a function of theta, and so you see that that the spatial walk-off is directly related to the bandwidth with respect to theta. So the bandwidth that we were looking at so far was on frequency, right? And now you can also look at the bandwidth or at the acceptance interval of for different angles, so which basically defines how critical this. So if we speak about critical phase matching, then we mean that the angle that we use is critical. So it must be adjusted very, very precisely. And of course, the flatter this curve is, the more critical this would be. Yeah, because a small deviation in angle leads to a strong reduction. So let's show this once again at these tuning curves. So if you look at this, here we have the angle, and now if you look at this example here, there a very small change in the angle leads to a large reduction in efficiency. Yeah, so on the other hand, where this curve is pretty steep, there if you change this the angle a little bit, then the efficiency doesn't change a lot. On the other hand, you need to hit precisely the wavelength, so you have a very small bandwidth here, right? Okay, yeah, so spatial walk-off. Spatial walk-off and angular bandwidth are closely related. As apparent from the factor dn over d theta in the equation, in the above equation. Good. With this, we look at temporal walk-off. We discussed it already, but we want to write down a few words also on this. So temporal walk-off so it's clear that not only the refractive index for shorter wavelengths is larger, but also the group velocity goes down, which means that after a while, if you have pulses, the second harmonic will lag behind the fundamental. And then you have pretty much the same situation, even so both beams may be perfectly on the same, perfectly collinear. There's nevertheless a walk-off in direction of the beam. Quite often you have both, of course, right? If K is not parallel to the principal axis of the indicatrix, and you use short pulses, then you have spatial walk-off and temporal walk-off at the same time. So for short pulses, yeah, the pulsed fundamental and the pulsed second harmonic may separate along the beam path. Because the group velocity of the blue pulse, so colloquially for the second harmonic of the blue pulse is smaller than the group velocity of the fundamental of the red pulse. Yeah. And again, the group velocity is just the derivative of k with respect to omega. So, or the inverse of that actually. Yeah, so d omega over dk. So, and if you would calculate that, then you find then you find c over n minus lambda dn over lambda. Yeah. So, and then we can easily calculate the spatial separation. Yeah, so the spatial separation we call it delta z is then given by, has of course to do with the time over which we propagate. So this would be delta z is just the difference of the group velocities times t, and and this will lead to, so if we use the speed of light, then we will get c squared over tau. This is the pulse length. We would write here actually delta L. Yeah, so so if you have a certain pulse length tau, then after distance delta L, both pulses would be separated, and this is then given by this formula here. Well, an example for that, again KDP. And again at 693 nanometers, and what you find there is delta L equal to 0.9 millimeter. Yeah, so this is quite short. So in principle, it's possible to compensate this effect by putting nonlinear crystals in a clever way together, such that walk-off goes once in this direction and then in this direction, and you could do the same thing for temporal walk-off. But this is, of course, complicated, and people would usually try to avoid that. So one thing now on non-critical phase matching, we mentioned that last time already. So what I would like to, what's that here? What I would like to introduce here is a famous person, and actually I think he should be more famous than so he's hardly mentioned in nonlinear optics textbooks, but he is actually the inventor or the discoverer of a few important nonlinear crystals, most notably BBO, which is a very efficient nonlinear crystal, and also LBO, which is an important crystal for non-critical phase matching, right? And so he's of Chinese nationality, and was actually working throughout his life on looking at the chemistry of these crystals and finding new nonlinear crystals. And well, without his work, I think nonlinear optics would be in a much worse shape than it actually is. Here's a particularly interesting KBBF for whatever it stands. Well, there's potassium, there's fluoride, oxygen, borium, beryllium. So a complicated compound actually. And this crystal is very important because you can do nonlinear optics at short wavelengths with this crystal. All right, so there's a very limited choice for these kind of for short wavelengths. So it goes down to the deep UV. And for many years, he was the only one who was able actually to produce these crystals. And at some point, this got relevant for the military. I'm not sure for what application exactly. And then, of course, other nations, most notably the US, they put a lot of money into establishing their own production of this crystal. Well, one final thing on phase matching, and this is quasi-phase matching. So if we look once again at what happens in phase matching, you remember this this small figure from last time. And then if phase matching is not perfect, then we are no longer in phase with, so then the second harmonic and the fundamental are no longer in phase. So you see that here the zero transition was the same, but then it goes out of phase, right? This would lead, of course, to the situation that the second harmonic then would transfer energy back to the fundamental. So what can we do in order to avoid that? If things like critical and non-critical phase matching is not an option. And there are actually interesting crystals, gallium arsenide, for example, and Lysium Niobate is another example, where non-critical and critical phase matching don't work. A particularly important instance is if you want to use in the susceptibility tensor so an element on the diagonal, so say chi 3, 3, 3, then this means that you have to use the same polarization for each of the 3 colors, and this means automatically that you can't exploit birefringence even if the crystal is birefringent, right? Once again, there are situations where non-critical phase matching and critical phase matching doesn't work because birefringence is not strong enough, or because you want to use a tensor element that mixes only the same polarizations. And the tricky thing is actually that this chi 3, 3, 3 component quite often is the by far strongest nonlinearity. Yeah? Okay, so what then can be done? So now here is the idea. So what we could do is just to wait or just to use the thickness throughout which both colors are reasonably in phase. We have learned already that this would be the case for just a few micrometers. Yeah. So after you would make your crystal just a few micrometers thick, and then you would let it propagate through some other material where no interaction between these 2 waves takes place, say just a piece of glass, right? And you would wait until well, they are out of phase, and finally they get in phase again, right? Would just make this, would choose the appropriate thickness. And then you would put another piece of this nonlinear crystal, another few micrometers of, say, BBO, KDP, or whatever you want to use. And after that, you would put the next thing here in, right? This sounds, of course, yeah, demanding to produce this yeah, in an optics lab or so, because dealing with micrometer thin plates, this would be very cumbersome. Well, fortunately, there are other options for certain crystals. Namely, if you have a crystal, well, let's go to this one here. Yeah, so this is Lysium Niobate, and this is a ferroelectric crystal. What is a ferroelectric crystal? Does anybody know? No? Yeah, so for magnetic materials, we know that, yeah, so for paramagnetic materials, yeah, so we know that there are these currents, these circular currents, they produce a magnetic dipole. And if these magnetic dipoles interact strongly, then we have a ferromagnet. Yeah? So magnetic dipole plus interacting magnetic dipoles, this gives some ferromagnetic material. And ferroelectricity or ferroelectric materials, there you would use an electric dipole, and if they interact strongly enough, you would call it ferroelectric. Right? And this is the case here for this Lysium Niobate. The interesting thing is actually that you can, yeah, so they are, well, for every dipole there's a direction. right? And so by turning this crystal around, you can invert this dipole moment, and therefore you would also change the phase with which you create the second harmonic. And with this, I go back to this slide here. And if you look carefully here, you see here arrows indicating, say, the direction of the electric dipole moments, and you just would put another crystal here where the direction of these arrows is inverted. So a little bit hard to see, but this is the idea. The question is just, how can it be done technologically, right? And what you can actually do is to apply a large electric field. So here you have this Lysium Niobate crystal, and then you would put electrodes on top of it, here a photoresist, so that you can structure it very nicely. And then you have an electric, you have a strong electric field here, because the photoresist is an insulator. You don't have it here, and you would apply high voltage. And then it's actually possible to change the direction of the dipole moments. And this here is a phase contrast image of a periodically poled PP Lysium Niobate, piplin in the slang of nonlinear optics. So a very nice method. The idea is 50 years old or even older, but it took a long time until some bold PhD student took it seriously, this idea. I think it was only in the 70s or so, or 80s even, and made it, so rendered this idea into some product. And nowadays you can buy these periodically poled Lysium Niobate crystals. So they are typically just a slab. You can't make them very thick because you need a strong electric field, and the thicker you make it, the more problematic things would get. Okay, well, so this is just another graph here. So let's write that down. Quasi-phase matching. So we have 6, it was 6.7, so we have now 6.8, chapter 6.8. Quasi-phase matching. QPM as an abbreviation. So, phase matching based on birefringence is not always an option. So, and reasons are the nonlinear crystal if the nonlinear crystal does not exhibit birefringence. Or not enough. Or you want to use say high 333, yeah? Which means yeah, so this means that all three waves have the same polarization. The same polarization, yeah? Yeah, and one remark here, quite often high 333 is the by far largest component. So then quasi-phase matching, then QPM is the only remaining option. Yeah, and the idea is choose the length of the nonlinear medium, choose the length of the nonlinear medium to match or to be shorter to match the coherence length. And then either use a medium that does not mix the waves, or, and that is the better idea if available, or change the polarization or the sign of the polarization. Yeah. So the most well-known example is Lysium Niobate. Is Lysium Niobate. And it's called PP. So this is so there's of course also a disadvantage of these nonlinear crystals, namely that the power they can take is limited to less than a watt. So you have I explained already that these are thin slabs of this material, and this automatically means that the power that they can accept is limited. I guess that also this this poling would be destroyed if this crystal is used at too high temperature intensities. There are many other instances in nonlinear optics where people speak of phase matching or quasi-phase matching, and I would like to briefly explain one example, namely that you just phase match or try to do approximate phase matching in a focus. Yeah? So if we take a laser focus, say something like this, a typical Gaussian focus, then we know that the phase changes in this focus, right? So the phase goes like what's called the Quasi-Face. Maybe I use a different color. So typically something like that for a monochromatic wave. So this is the Quasi-Face. Now, what you see is that say the harmonics that are created here are out of phase with harmonics created here. Right? So usually the creation of the harmonics would be restricted more or less to this region. Now, there are situations where you can take advantage of that, and one of them is actually high harmonic generation. Yeah, so high harmonic generation means that we have, so that we just have some gas here, right? And each of these atoms would produce harmonics, right? And now the goal is to make sure that the phase of say a harmonic that is emitted by this atom matches the phase of a harmonic emitted by this atom. Yeah, so when the harmonic emitted by this atom arrives here at this atom, then the phase of both should be equal, right? Now, if we produce high harmonics, then we use very high intensities for that, and this means that we also ionize this medium. Yeah? So, and what we then have is free electrons. We have the gas here. We have the different phases due to the different phase at which these atoms are excited, right? And now we have the situation that an atom that emits a harmonic here, yeah, so a given harmonic here, say the 35th harmonic, does this with a different intensity here as compared to here. All right, so the harmonics, the same harmonic is created by a different intensity at different places, which implies, or which can imply, that the phase of these harmonics is also different because of the different intensity at which the harmonic is produced. We will look at this in some detail in the next semester in a lecture on strong field laser physics. So we have here 4 ingredients. Once again, just the material, the gas itself, then the free electrons that are created. They also have a refractive index. Then the phase here, the Quasi-Face, and finally also what's called the atomic phase in this case, namely the fact that the harmonics are created at different intensities and therefore may have a different phase. Yeah, complicated story, phase matching and phase mismatch, but a very important thing in nonlinear creation of new frequencies. I think it doesn't make sense to start a new chapter, and therefore I would stop at this point for today. We would continue next year. I think, yes, but unfortunately in Thuringia we are Protestants, right? And therefore the 6th of January is not a holiday, and therefore lectures start already on the 3rd of January. So we would meet on the 3rd of January again. And what we will do next year is to look at third-order processes. We introduced them already in chapter 2 when we gave an overview of different nonlinear effects. And we will first look at what happens spatially. Self-focusing is a key word. But then we will look particularly at what happens if we use short pulses. So we will look at the nonlinear propagation of short pulses. And in order to be able to understand that, it is of course important that you learn something about the propagation, the linear propagation of short pulses. Yeah? So if you have a short pulse and you propagate it through some medium, then the pulse typically gets broader. And I've prepared a chapter on the linear propagation of short pulses, and I would like to encourage you to review that chapter. I will upload it to Moodle. So it's a pretty long chapter, actually. But it is linear pulse propagation, so it doesn't belong to this lecture. But you nevertheless need it. So I hope this is something that you find enjoyable under the Christmas tree. So with this, I close this lecture. Thank you for your attention.